Good afternoon, everybody. Unfortunately, I was not able to join the class, so I'm recording my presentation. My name is Ali Marar, and I'm presenting my final project for power system detection estimation. And my project is a distributed state estimation algorithm utilizing matrix splitting. A little bit about myself and motivation behind this project. I'm an electrical engineer in Jacksonville, Florida, working for a utility. I've had the opportunity to work with solar generation, natural gas, and coal, and we can see what the differences are between each one. I have the opportunity to do long-term and short-term planning on the power system, and the opportunity to work with SCADA field devices as well. So I'm a little familiar with a lot of the different devices and architecture behind these. And I've also had the opportunity to delve a little bit into FERC and the FRCC regulations that they have. My interests include both power system and computing, so I'm trying to utilize both into this project. I just want to quickly go over the need for PMUs. As you all know, the power grid supports critical infrastructure, including communication networks, fuel, and water supply systems. If the reliability of the power grid is hindered, then the chances of losing these systems is higher. And so what we want to do is we want to utilize PMUs to prevent blackouts and upgrade the aging system. Most components of the power system power grid have not been updated since the 1970s. We're still utilizing old technology. So PMUs will allow us to realize a robust, efficient system, and will allow us to provide monitoring for our increased renewable energy production. As you all know, renewable energy is a function of physical conditions, including weather. So it is important that we monitor renewable energy in a little bit more depth. We also want to provide real-time operating conditions to power system operators. So I just want to quickly go over high-performance computing as it does relate to my topic. High-performance computing is the use of parallel processing techniques and or high or hyper-performing processors to achieve more efficient, realizable, and faster results. So, what we're using is multiple nodes to achieve our, to split our calculations per se, to perform the calculations at a faster rate. It's a little bit similar to the cloud-based model where processes are delegated to nodes such that computing is not accomplished only at a central location. I want to go over why high-performance computing. Utilities utilize old computing methods to achieve results. And typically the computing is done at a central location, which is undesirable. Typically that central location is where the system operators are working out of, and that's typically where these servers exist. And in the age of data that we live in, and as we rely more and more on data to make decisions, the more robust data there is, the more computational power is required to take advantage of the data. So if we continue to use these old computing methods, we will not be able to efficiently and advantageously use our data. PMUs provide high sampling rates, and with that, we need more computational power to utilize influx of data. PMUs can provide data at a magnitude of 100 times more than what a SCADA device would due to the higher sampling rates. So if we want to utilize PMUs to their maximum, we need to also realize that we need a high performance computing scheme to do these state estimation. And since state estimation is a statistical approach, the more data taken into consideration, the lesser the variance will be, yielding more accurate results. Some considerations and challenges to keep into account and that I faced during this project is lack of power system data. Since power system data is considered proprietary, it's typically data only from research is found. A lot of the utility data is not published, so it makes it a little bit difficult to benchmark our results. Another thing is there's a lack of strong communication networks for utilities. Therefore, PMUs are not being deployed due to not having communication or the large cost associated with having a strong communication network. And I've faced that many times when implementing even SCADA devices. And there's a lack of qualification, as utilities typically hire power system engineers, and there's not much data scientists or subject matter experts in communication. There's a lot involved with more than 240,000 miles of transmission lines. There's a lot of monitoring to be done, and a lot of times things go missed. So now we'll begin to discuss our project in depth. Our interest here is a decentralized distributed algorithm. The power grid itself can be modeled with vertices, nodes, or buses, and edges, which are which basically is the parameters of the transmission system. Since state estimation is a statistical linear algebra model, matrices and more specifically matrix inversion tends to be the bottleneck in terms of the calculation. The size of the matrix itself is directly correlated to the number of edges in the system. So if we have a large system, that means the inversion will become large, causing a bottleneck on the computing side. So utilizing a decentralized approach, matrix inversion can be done more efficiently while still taking into account the system state estimation runs in real time. And since state estimators run in real time, it is important to consider that we need to try to converge the function or the state estimation function as fast as possible, such that we can bring in the next time period. So I've got a figure here that basically shows this yellowish orange color shows our decentralized approach, where each node talks to the next node and the computation is being done, rather than in the green here where the nodes are sending their information back to a central controller, and that central controller is taking care of its tasks at hand. So what we're proposing is a matrix splitting method, essentially solving a system of linear equations. Matrix splitting ensures convergence. Each vertex calculates its own estimate of its state. State information is exchanged amongst other vertices, and both PMU measurements and SCADA measurements are used. And in reality, I've never seen a system that it's strictly PMUs. Typically, SCADA is what's being used right now. PMUs are being brought in. So we want to use PMUs to, and we'll show that in our results, to provide more accurate results when combined with SCADA. Each vertex is responsible to retain its own state estimate rather than a global system. And communication and memory resources are freed this way, that because we're not dumping all of our data into one hard drive or one central location. So our problem statement for this project is going to be utilizing PMUs in computational science to enhance state estimation techniques that in return improve monitoring of the power grid. The goal of the state estimation or state estimator is to determine the unknown voltages, both magnitude and phase angle at each bus or vertex from the set of available measurements provided by PMUs and SCADA. So given the noisy system parameters or measurements, Z, basically the input to our state estimation problem, the state X, both magnitude and phase angle, will be determined at each vertex in the model. Basically formulated as a weighted nonlinear least square optimization problem, which is our objective function. The objective function is the weighted sum of the residuals, where the input Z is then related to X for a nonlinear function H. So what we're saying here is we will determine, utilizing this objective function, we will determine X through the input Z, which is utilizing H, a nonlinear function. And we will solve through iteration using the Newton method. And what's important to consider here in the Newton method is the part of the formulation is grad squared f times f. That tends to cause, that's the matrix inversion of grad squared f causes the bottleneck when it comes to the calculation. So what we want to do here now is we want to introduce how we will do the matrix splitting, which is, let's take, for example, matrix A. We'll take matrix A and split that into the sum, or matrix A becomes the sum of matrix M plus N. And as you can see here, A is then equated to the grad squared F. And what we'll do is A becomes the sum of D plus E, D being the diagonal part of A, and then E being the non-diagonal part of A. And we'll add an E bar to each parameter. And E bar is basically a constant here, and it's added to D, but subtracted from E. So in reality, it makes up for itself. And those are set to be called M and N. So to move on, matrix M is the diagonal part of matrix A, or grad squared F, and matrix M would invert seamlessly since it is only a diagonal function, diagonal matrix. Now, diagonal, or the matrix N, which is the non-diagonal matrix, is where we will have some of the computational challenges. But we can simplify that by utilizing Kirchhoff's current and voltage laws, as they still take precedence in this case. And so matrix N utilizes the topology as illustrated here. If in sample A here, or figure A, we want to compute the voltage measurement, both magnitude and phase at A, we can set our PMU at A and measure that directly. And that information can be stored directly at A. Now in the case, if we go to figure B, where power flow is being estimated between node A and node B, the power flow will require information from both A and B, and will perform its state estimation to calculate what the power flow would be in between. Node A and node B are expected to have their information at each node. And if we look at the third figure here, where power injection at node A is being calculated, the formulation for power injection requires that information from node A, B, and C be present. So node B and node C would communicate with node A and send over their results. But in all reality, what is to be taken from here is that each node stores and calculates its own results as it needs, and not sent back to a central controller and then sent back to the node. So we'll go over some pseudocode real quick. We'll initialize our variables and set the state estimation vector to x to be for the phase angle to be 0 and the magnitude to be 1, and we'll enter the loop and we'll set the current state to 0, and we'll enter the next loop to calculate to utilize the matrix splitting inner loop to calculate the current state. And once the current state is calculated, that would be communicated with the neighboring nodes. We'll exit that loop, and then we'll communicate with, we'll begin to calculate the next state, and then we'll communicate that with the next neighbor. So the inner loop is where the very inner loop is where the matrix splitting occurs, and then and like I said, the Newton method only still takes precedence and is in the outer loop. It's a little confusing, as you know, when you nest three loops together. But we'll use the to prove our methodology, or to further illustrate, we'll use the IEEE 14 bus as an example here. Let's say that we are looking to find the phase angle measurement at bus 2, or node 2. Node 2 is connected to 3, 4, 5, and 1. And what we'll do here is that we'll communicate with the nodes that that neighbor us, per se, and in this case it's 1, 5, 4, and 3, receive results and perform the calculation to find the phase angle measurement at node 2, rather than having to send all of this data back to a central controller for the entire system, which can cause a bottleneck on communication as well, since a lot of stuff is being sent back. Calculate what needs to be calculated, and then relay that information. So the results of this project were a little interesting. I use a 14 bus, 118 bus, and a 390 bus network that I found online. The 14 and 118 are the IEEE utilizing IEEE methodology. As you can see, on the runtime on the 14 bus is actually, before we go into all that, let's take a look at what what our graphs show. So it's basically objective function versus the new iterations, or the number of matrix splitting / iterations are taking place. 14 bus network converges as its limit goes to infinity, which is a good thing to have. Same thing with the 118 bus network. We begin to converge as the limit approaches infinity. But as you can see, the convergence rate is a little bit slower on the 118 bus network, and that's mainly because the inversion matrix becomes larger and causes more lag on the computer. And then, as you can see, we have a 390 bus network, which, as it approaches, in this case, infinity or 40, it begins to slope, but it doesn't converge. And in fact, I was not able to converge the 390 bus network, unfortunately. I think it's a combination of two items. Number one, it was a model I found online, and maybe the model is just not very accurate. Another reason is because the computer that I'm using may not be the best computer for this project. As you can see below, you have the runtime. The calculation is at 1.5 seconds in both scenarios. What's taking longer, setting up the problem, and these were computed right out of MATLAB, specifically the runtimes, and plotted in Excel. So now our results continued, and this is part of the output from MATLAB as well, is we're going to take a look to compare our voltage angle and voltage magnitude errors with and without PMUs. So as we added PMUs to our model, we were able to increase or decrease the error with the state estimation technique. So as you can see, the angle error with a PMU is at maximum around 0.04, and without the PMU, we're at a maximum of around 1.7, 1.8. And same thing with our magnitudes. When we look at our with the PMU, the maximum error we're having is about 0.55, and without PMUs, we're in the threshold of 5.9 per se. And we have a magnitude of about a tenfold change in error. So PMUs do bring more reliable, as they bring more reliable data into the set. It forces the state estimation technique or state estimation algorithm to converge to more reliable estimation of the overall system. Just realized I went over 20 minutes. So to quickly conclude, an alternative to the iterative, we were able to provide an alternative to the iterative matrix budding technique as accomplished. So we were able to provide another method to solve the problem. Though our results were not the best when it came to the larger system, I think had there been more computational power or availability of a supercomputer per se, I think we were able to converge on that specific scenario and use those results to make our algorithm even better. I did see that limited sharing between vertices or buses results in a more efficient communication data exchange scheme. That way we're not exchanging, that way that all the information is not being sent to a central controller, but rather is only being exchanged between the different nodes. And we utilized, I guess, modern day computing architecture to solve a problem, which typically the power world and the computing world don't tend to combine or collaborate at times, let's say. So it's been fun doing this project, and I really appreciate a lot of the things that I've learned in this course. Thanks for your time.